So, hello everyone. Today we are going to discuss on the applied civil engineering theory. So that is basically bending, shear, beams. Uh, these two topics are more often used in analysis, right? So, if you move the basic introduction, if you apply a load to a particular beam, let's say this, right? It deforms, right? It affects you to bending, right? So it creates internal stressors, right? So we basically identify the shear force as the resultant shear parallel to the section, right? Along the section. So the resultant normal stressors perpendicular to a section, right, are identified as bending moment, right? So if you consider a simple equation, right? So we assume that these stressors lies within the elastic region. So we can use sigma equals E epsilon, right? That means we are well within the elastic region, right? So between sigma and epsilon, you have a gradual, right? So if you apply S equals, so let's consider this beam. So if we going to bend this beam, right? So if you consider this particular fiber is going to be compressed, right? Can you see this? This compared to this, let me draw this. Compared to this one, this length has reduced, right? So that means it is compressed, right? Compared to this length is increased, right? So that means it is under tension, right? So between these two surfaces, we have a neutral surface called where you not see any tension or compression, right? So you can apply uh, from this neutral axis, say this. So let's call this surface y below from the neutral axis, right? So we can call it S equals r theta. We can apply, right? Let's consider the r is the radius up to the neutral surface. Okay. So this length is r theta, right? It's r theta, right? So this additional, so this the length to the selected fiber, we call it y, right? So that particular length of the arc can be taken from this x equals r plus y into theta. So now the r radius is r plus y. So change in length, you can take from, you can subtract these two equations and check sy plus n minus sn is equals to y, right? So from your fundamentals, you know the strain is change in length compared to its original length. So this was the change in length. It was y theta. So it's y into theta, right? So the original length was r theta. So theta is getting cancelled. The strain becomes y over r, right? This is the bending strain, right? So if you apply F sigma equals E epsilon naught, where epsilon naught is now y over r, the strain stress equals Young's modulus into the strain, right? So we assume the stresses are well within the elastic region. Other, if it is going to the plastic region, you can't apply this equation, right? So there will be a permanent deformation in such case, right? This is your epsilon naught, the stress. You can see for constant stress, your epsilon naught is increasing, right? So you are working in this region, right? Elastic region, right? So we move to bending formula. So we call the resultant of normal forces, right? So the top fibers are in compression and the bottom fibers are in tension, and in between you have a surface where no tension or no compression is observed, right? So we can apply this, right? So we consider a particular area, right? Let's call this area. So there will be stresses, right? So what happens if you take a small area where you can think the stress is constant, right? Because with the depth it is varying, right? So you get a small area where you can see the stress is sigma, right? So stress into a area, stress into area is called force, right? So we call this EA area. So this is the force, right? This is the force, right? So we need to bend the moment of that particular area about the neutral axis, right? So we call this y distance away. So since this is a particularly small area, this y is equal to the centroid, to the depth from its centroid to the neutral axis. Don't need it is this thickness is negligible, right? So in that case you can write bending moment of this in strip is sigma EA to y. So that means force into lever arm, right? So to calculate the total bending moments, because sigma is variant along the depth, right? So you have to calculate that. So say sigma, so from the last slide, you obtain sigma is a function of y, right? So here as well, y is there originally from the lever arm, and when you substitute that, so you can take E over R out, right? So you will be remaining y squared EA, right? So if you know this, what is this on the first principle? This is the second moment of area. So here's this second moment of inertia. So it's simply called the resistance of a section due to bending. So resistance of a section to bending due to its shape, right? So you can see here I is 1. When you rotate it, I is 9. So that means this can more resist bending, right? So if you can just think a practical scenario. So you take a river and you construct a bridge. So what happens if your bridge is like this and you take the same beam and you put it like this. Right. So definitely this is going to deflect more. Why? Can you see theoretically? So if your I is low, right? I is low, so you can take this. It has a less resistance to bending, right? So to bend more. So you can see if your I is reduced, you have a your M is increased, right? If your I is high, so you particularly have a good resistance to bending, right? Due to its shape. So another term comes with this, which is called radius of gyration. What particularly it means? So let's use some complex equation, right? Rx equals to Ix over A, right? Just, just think about what is the physical meaning of it. You are dividing the whole I by its area, right? So that means the distance from the neutral axis where the particular area can be uh, condensed into a strip to get the same inertia. So I think you didn't understand that, right? Let me close. So if you consider some area like this is your x-axis field called. So let's call this is your object, and about x you have I. Call it I xx. So we convert it to a strip in strip, right? So these two have same inertia, right? These two have same inertia. So this distance is theoretically called Rx, right? You simply divide this I by its area, right? So that means the distance from NA, where the area, this area can be condensed into a strip to get the same inertia. So if you multiply this by, so this can be taken A R X squared, right? So from these equations here, B and A, you can determine this bending equation. This is the most important formula you ever remember, right? This is very advanced. So this is very beneficial in even design as well, right? So then we move into shear force, right? So we do the parallel forces, that means along a section, right? In this case. So, but another term comes, what is this complementary horizontal shear, right? So which basically means, let's say something like this. So, say some timber planks which are not glued together, right? If you apply a beam, if you apply a load, right? So these planks can move relative to each other as shown in this figure. But what happens if you glue them together? Then they no longer can move relative to each other. So that means there should be a resistance which is generated. What is that? That is called complementary shear, right? So you every day see this, right? You every day see this, but you have to understand the concepts, right? So generally, that's why the timber beams uh, have seen horizontal split horizontally near the center of the beam. That is the shear failure, right? The shear failure, horizontal shear failure, right? When you apply, so we try to move relative to each other, but now we have glued them. It idealized a simplified beam when that shear is larger than the applied resistance. So it's right. So now let's call this shear force is V at a particular section, right? So yes, you can check the average shear stress by dividing this B over this entire area. It's not a problem, right? That idealization is valid. But actually, shear has a particular distribution along its depth. So we'll consider a particular area is shaded by this area. This is the shear stress equation. Don't is complex, right? Now just look at those variables, right? So let's consider the shear stress of that particular area. Okay, so that means B is there, right? This is shear force, right? So this shear force, okay, is multiplied by this area, and then Qy is actually the first moment of area, so that is the area into the distance to center, right? So if it is d by 2, right? So let's call this y, then this is d by 2 minus y. The area is d by 2 minus y into b. Okay, area is correct. So how to get this distance? So we need to subtract y from d by 2 is this, and for that you have to take the middle of that, and that is d by 2 minus y, all thing divided by 2 plus y is the distance to the center. So that becomes d by 2 plus y, right? b to 2. This half is coming, right? So this is the shear force, first moment of area, y, right? So this is I, second moment of inertia. This rectangular portion is q or 12, and y is d. So if you simplify this becomes an equation like this. Can you see when your depth is changing shear stress changes, right? This, this becomes a maximum when this term is zero. So that means at the neutral axis, so that means centroid axis, your shear stress is at maximum. When this is d by 2, shear stress theoretically becomes 0 and looks like a distribution like this. It is maximum at the neutral surface and 0 at the extreme fibers. This is particularly different from the bending stress. So on bending stress, it is maximum. So sigma is bending stress, sigma equals my over I. So it is maximum at the edge fibers and it is 0 at the neutral surface. Here for a rectangular section, it is maximum at the neutral surface, but in the meantime it is the lowest, that is nearly 0 at the extreme fibers. Right? So you can take that maximum value when y equals 0. It is 3e over 2ed. That means 1.5 into this. That means it is 1.5 into average shear for a rectangular section. This might not be the same for another section, right? But you can derive from the first principle. So if you check the bending and shear curves, right? So you know this relationship dV over dx is minus w, which means load, the area under the loading diagram shows you change in shear between 2 points, and the area under a shear force diagram between 2 points gives you change in bending moments at those 2 points. If change is 0, we call it the pure bending. That means the beam has uniform bending moment throughout that length where shear force is 0. Right? So, what is this applicability of these processes and other things? Do we actually see it? Yes. Yeah. So, we can see this example, right? So they have given a simply supported beam with uniformly distributed load, right? So if you consider this, right, W, so it's 28 and it is simply supported with W by 2, 28, so L is 2. Okay, so the maximum bending moment is W squared over 12, 40, right? So the maximum shear, you can take the average shear. So they usually take maximum shear d distance from the support in the designs, right? That's a reason, right? So if you consider the d distance, okay, so you can take it from the similar triangles. So your shear at d distance will be 20. Shear at the ends is 28. Okay, it's not the shear usually taken for a design, right? So if it is 2 and 3, let's call the shear force. Okay, so you can take what is the maximum shear stress. This is the average shear. Then you divide it by the area. Okay, so this is for kilonewton to become 6 Newton. Okay, turn into millimeter squared. So that brings you 1 megapascal. So that means 3 shear force is 20 kilonewton. So that means 1000. That becomes the numerator in Newton, right? 2 into area. Area is how much? I think it has yes, D is not showing. D is 300 and it is 100. I think the font is not showing. Done. So it's 100. 2, 3. So that brings to 1 Newton per minute. So this equals 1 megapascal, right? So then it is for this. It is for this element. Shall we see the element? So that is soon draw it. It is n. This was the support, right? Somewhere about this element, right? So it has some shear force, right? So we call it that maximum shear is in the downward direction, right? From the complementary shear, you should know it should make the other cover, right? So consider the equilibrium, the shear force should be in the upward direction, and this couple is in clockwise, this couple is in anti-clockwise. Now, element is in equilibrium. Is 1 megapascal, right? So how do we analyze this? We can simply draw. Actually, we use mohr, right? So you consider this element. It's positive. We will get tension. Tension is positive. So we can draw a mohr, simple mohr, right? This is rho. It's normal stress. So you can see in this phase, you don't have any normal stresses. Why? Because you don't have any bending stress, right? Bending stresses are normal, right? Those are maximum at edge fibers and becoming zero at the neutral axis. So if you consider the neutral axis, bending stresses are zero. So that means you do not have any normal stress on this element, right? And the other thing is this bending stress there is on the length as well. So bending becomes more significant towards the middle of the beam. Why? Maximum bending moment like this, right? Is maximum at the middle, right? It is zero, almost zero at the ends, right? So shear is maximum at the support, right? The support. Usually we take the average shear, right? So, but if you consider maximum shear stress distribution, so here I did not draw any distribution because the average shear is something and the maximum shear stress is the actual, right? So for this circle, we call this shear. That's why we take some element close to this support where the shear is at maximum, right? Shear is maximum closer to the support, right? So this is the maximum shear stress on this element is, right? That is 1. And the normal stress is 0. So that brings you to this point. And here it is, so we call this clockwise shear positive. Okay, so this is anti-clockwise shear, and normal stress is against zero. So we can draw more circle. So this intersecting point sigma 1, sigma 2 are the principal stresses. Can you see when the principal stress is occurring, the shear stress is zero, right? Those are the maximum principal stresses that element suffers, right? But it changes with the element configuration. So here you are on the surface. If you want maximum stresses, you need to go this configuration. So that means you need to go 19 anti-clockwise direction, right? So you have to rotate this element by some amount in the anti-clockwise direction. But you know, the theta corresponds to mohr circle is twice that of the original object. So if it is 19 the mohr circle, it is 45 for the original element. So that means you need to rotate this element by 45 in this direction, right? So that brings you here. You got, so this was the original element. So this surface is now rotated 45 amount, right? 45 degrees. So at that you have sigma 2 negative. So that means it is in compression, right? Our sign convention is tension positive. It is in compression, and if you go to the other surface, it is 90 degrees. So that means 180 degrees in mohr circle. It is sigma 1, and this radius is 1, right? So this radius also 1. So this is also then 1 megapascal, and this sigma 1 is positive. So that means it's a tension. So just consider, if you apply a compression to like this, you push like this, and you put it like this, you can have cracks due to this tension like this. You can tear this element like this due to this like tension. Right? That's why you usually get shear cracks diagonally. These fundamental process, right? So you can actually identify that using a simple mohr circle, right? These are the principal stresses. This is the principal configuration, right? When it is rotated by 45, your sigma on these stresses, normal stresses become maximum, and shear stresses become zero, right? So that's why you have diagonal cracks. So even it can be verified using experimental values. So it is the same thing. Okay. You should know these shear failures are very sudden, right? At P2, failure type is more critical. Can you see, if you load something like this, can you see these diagonal cracks? These are shear cracks near to the support, right? So we simply idealize using a simple mohr circle and the element. But the same thing can be done even for flexure. So the flexure becomes critical towards the middle of the beam, and we know that is critical at the end of at the edge fibers. Here it is compression and here it is tension. So we will take the tension element. Okay. So we have taken it is sigma equals m pi over I. Okay. So that brings they have bending moment, W is 8, and this y is I, second moment of inertia. So this is 1 megapascal, right? So if you consider this beam, right? So now shear was maximum at corners and is maximum at the middle, right? But the bending becomes critical towards the middle, and you have maximum compression at the top and the maximum tension at the bottom. Usually concrete is the tension. So we will take an element near to the near to the bottommost fiber, right? So we call this element. So now the fundamentals. What is the shear stress distribution? How it varies with height? So you remember shear is almost zero at the edge fiber. So that is the bottommost and topmost fibers. So that means this element does not have shear contribution, right? So it will only have this bending moment. It's compression and tension. So it will have a tensile stress. No shear, it will have a tensile stress. And it won't have any on its surface as well. It doesn't have any normal loading. Okay, it doesn't have any complementary shear because this element should be in equilibrium. Do not have any normal forces. Okay, so this element have this tensile stresses. Right. So we can draw this in a more circle too. So it is tension and zero, right? It is some value and zero height, right? So we were in here, right? In the mohr circle. In this element, we have tension and zero shear. And it's 90 degrees, right? You take this 90 degrees in this element. So that is 180 in the mohr circle. We have zero normal stress and zero shear stress. That brings you to the origin. So you can draw like this. So from that moment, so since your shear stresses are zero, that automatically becomes your principal stressors, right? This is the principal tensile stress. Let's call it sigma 1, and this is sigma 2, this is 0. element does not have any compressive stresses, right? So such kind of element, so you can see, if you try to pull it from apart, it will tear like this, right? It will be cracked like this, right? Because the bending moments are significant at the end of each edge, right? Each section, and it is zero at the neutral axis. Okay, it is completely different from the shear distribution, right? So this is also actually visible. So can you see these are the flexural cracks? Those are vertical, right? Normally vertical, going bottom to top. Why? At the bottom, there you have maximum tensile stresses, where your crack initiates, right? And near to the support, so in here you can see flexural and both shear cracks, flexural shear cracks, right? And at the support, usually you have diagonal shear cracks, right? So these bending cracks are not sudden. Okay, those are ductile type, right? So it appears and gradually increase. Shear failures are sudden; they they happen at once, right? So you saw even in this small circle, we could identify these idealized simplified scenarios where it could practically be seen in the experiments as well. So thank you very much.